In this video, we're going to continue with the Computer Science 9618 AS level. So we're going to be taking a look at logic gates and logic circuits. This is going to be a two-part video. The first video is getting a basic understanding of the logic gates and how they work. And the next video, we're going to take a look at some complex logic circuits and some practice problems. So let's go ahead and take a look at the learning targets to see what we need to be on the look for. So candidates should be able to do the following. They want you to be able to use a NOT gate. They want you to be able to use an AND gate. They want you to be able to use an OR gate, a NAND gate, a NOR gate, and an exceptional OR. And you need to be familiar with these symbols because when you draw your logic circuit, you're going to need to use the appropriate symbols. So they want you to understand and define the functions of all these gates and to construct the truth table for each of the logic gates above. Now all the gates except the NOT gate will have two inputs only. So let's jump in and let's get some background info. Now there are only two possible states for each input. 1 and 0 because those are the binary numbers. 0 means off and 1 means on. A switch can only be one or the other. You can't be on and off at the same time. It's like a TV remote. When you push the power button, it's either going to be on or you're going to be switching it off. It can't be in both states at once. Now, I have listed all possible combinations below when two inputs are being used. So we have input A, input B. We have A 0, 0, 1, 1. B is 0, 1, 0, 1. These are all the possible combinations, and there's a pattern here. 2 zeros, 2 ones, 0, 1, 0, 1, and in the next video we'll talk about 3 inputs. But these are all the possible inputs, or all of the possible combinations there can be when there are two inputs. All right, so let's learn the AND gate first. The Boolean expression is A dot B. Now notice there is a dot there. It is read as A and B. And the period, the dot there, means and. So the output will be true only if A and B are true. So we have an AND gate. Let's run each row and let's fill in the output. Okay, so we have our A input, we have our B input, we have our AND gate. I know this is an AND gate because it has that specific AND gate shape, and we have our output. So we're going to connect A, we're going to connect B because it's going through the AND gate. We said both of these must be true in order for the output to be 1. So right now the light bulb is off. So when both of A and B are state 0, we get an output of 0. The next thing I want to try is just B on. A is 0, B is 1. We can see that the output is still 0. My next trial is what if A is 1 and B is 0? So I turn A on and we see the output is still 0. But looking at the AND gate, it said both A and B must be true in order for the output to be 1. So I flip both of these switches and we can see the output is 1. Let's go fill in the truth table. And now we can fill in the truth table now that we've seen the results. So when A and B were both 0, meaning they were both off, it gave us an output of 0. The light bulb did not light up. What about when we just turned B on and left A 0? We didn't turn on A, we just flipped on B. We noticed we didn't get the light bulb to light up, producing a 0. What about when we just flipped A on and left B off? We also got an output of 0. But for the AND gate, both A and B must be true. And when we set both of them to on, we get the result or the output of 1, meaning the light bulb is going to light up. Now there are a list of gates you need to know. You need to be familiar with the AND gate, which we just went over. You need to be familiar with the OR gate. You need to be familiar with the inverter, which is also known as the NOT gate. You need to be familiar with the NAND gate. You need to be familiar with the NOR gate. And you need to be familiar with the XOR gate. So we're going to go ahead and go over the rest of these so you can get a firm basic understanding so we can move on to the advanced truth tables and advanced logic circuits. So let's learn the OR gate. So with the OR gate, the Boolean expression is A plus B. So notice the plus sign. We don't have a dot here. We have a plus sign. So it is A plus B. Now it's read as A or B. The plus means OR. Now the output will only be true if at least one input in the expression is true. In the case of A or B, or A plus B, the output will be true as long as at least A or B is true. So let's go to our diagram and see the results. So I have my inputs again, A, B, and what I'm going to do is I'm going to connect them. And we're going to connect this to our output. Now, notice both of them are in the state of 0. We are getting an output of 0. Now with OR, a lot of times when we hear that, people they think it's going to be one or the other. With OR gates, it can be one or the other, but it can also be both of them. So let's try just A. We try A, we see we get an output of 1. What if we just try B? We get an output of 1. What happens if I turn on both of them? That should work as well, and you can see we have an output of 1. Going through those trials, let's go back and let's fill out our truth table. So we took a look at the gate setup, and when A and B, when both of them were 0, we got an output of 0. The light bulb did not light up. What about when A was 0 and B was 1? Is at least one input true? Yes, and because B was true, which satisfies at least one input, we got an output of 1. What about when A was on but B was off? That satisfies the condition of at least one input being true. That gives us a 1 in the output. And what about when A was 1 and B is 1? Because we have A or B. But remember, with an OR gate, as long as at least 1 is true, it will give us an output of being true or an output of 1. It does not have to be one or the other. That is with the XOR gate, which we'll get to momentarily. Let's move on to the next gate. So the next gate is a NOT gate. And with a NOT gate, there's only going to be one input. And so we just have input A here. When A is 0, all we're going to do is simply invert it. This is read as not A. It's shown as A with an apostrophe or A with a line over it, like this. You can see an A with a line over it. That means not A. It inverts the value of the input. So let's take a look at this gate setup and then come back and fill out this truth table. So I have my A input. I'm going to run it through the NOT gate. Now notice the NOT gate or the inverter is in the shape of a triangle with this little dot or this little open circle right here. I'm not talking about these open circles. That's where the wires connect. But if you look at the tip of the triangle, you will see that there's a small little circle. You need to make sure that you're familiar with that and that you draw it on your exam if you need a NOT gate. Now you'll notice right away, we're getting the light bulb with an output of 1. It's lighting up because A is 0. When it goes through this inverter, it inverts the value of 0, becoming 1. When I turn this on, it will turn off. I'm getting the value of 1. It goes through the inverter and changes it to 0. Let's go back and fill out that simple truth table. When A is 0, not A is going to give us an output of 1. When 1, we're going to get an output of 0. Why? Because not A, 0. What is not 0? 1. What is not A when A is 1? Well, what is not 1? That is 0. Let's go ahead and move on to the next gate. And that next gate is a NAND gate. Okay, so this can be a little tricky at first, but think of it like this because that's what it is. It's technically an AND gate directly followed by an inverter or a NOT gate. Now it is read as the inversion of A and B. So you're taking the value of A and B and you're flipping it. This is what it looks like. Now notice there's a line over the entire thing. So the easiest way to do this is figure out A and B and then invert those values. Now the Boolean expression is A dot B with a line over the entire thing as seen in this example right here. So let's take a look at this gate setup and see how it works. I have my input A, I have my input B. Let's go ahead and connect them to this NAND gate. Now let's go ahead and take a look at the values going through this AND gate. And notice we have this inverter, this little circle on the end. That's how we differentiate between an AND gate and a NAND gate. Those are two different symbols there entirely. So make sure if you're writing an AND gate, you put this little circle here on the end so your examiner knows that you are distinguishing between an AND and an AND gate. So if A is 0 and B is 0, it goes to the AND gate. What is the value of A and B when both of them are 0? It gives us a value of 0. But then that 0 hits this inverter, changing the 0 to a 1, and that's why it lights up. Now what about if A is on and B isn't? It also lights up. Why? Because A is 1, B is 0, going through an AND gate, that gives us the value of 0, but then that value is inverted. Well, what if I just turn on B? It also works. A is 0, B is 1, going through an AND gate, that gives us 0, but then that 0 hits this inverter, giving us an output of 1. Now if I turn them both on, going through an AND gate, that would be a 1, but it's going to hit that inverter, changing it to a 0. Let's go back and let's fill in this truth table. So the easiest way to do this is to figure out A and B and then invert those values. That way you're not trying to memorize those values because it's literally not A and B. So we're inverting the values of A and B. So let's go ahead and review that AND gate. When A and B both have an input of 0, we get an output of 0. When just B is true, we get an output of 0. When just A is true, we get an output of 0. But when A and B are both 1, we get a value of 1. And when I write this off to the side on my exam, it makes it much, much easier for me to fill in the values of not A, B. All I'm going to do is I'm going to say not 0. Well, when A and B are 0, what's not 0? That's the value of 1. When A and B are not 0, that's the value of 1. When A and B are not 0, that's the value of 1. When A and B are 1, what is not 1? That is 0. And we just went through all those combinations to take a look to see how it works. Let's move on to the next gate. Now our next gate is the NOR gate, and it works very similar to the NAND gate. It inverts the values of the OR. So it's technically an OR gate followed by an inverter. Read as the output is true if both A and B are not true. Now the easiest way to do this is figure out A or B or A plus B and then simply invert those values. The Boolean expression is A plus B with a line over the entire thing. So it would look like this, A plus B. There is a line over the entire thing including this plus sign. This is not the same thing as not A or not B. This is A nor B. So let's take a look at this gate setup. So I have my input A, I have my input B. Going to connect these. Now notice I have my NOR gate. How do I know it's a NOR gate? Because it's in the shape of an OR gate with this little circle on the end, and that is an inverter. Now when A is 0 or B is 0 going through an OR gate, that gives me 0. But then it gets inverted, and that gives us a value of 1. And we can see that is what happens. But what about if I turn A on? Well, when A is 1 and B is 0 going through an OR gate, that gives us a value of 1. We hit the inverter, which gives us a value of 0. When I just turn B on, I still get that same result. Going through an OR gate, this would give us a value of 1, but it hits that inverter, giving us a 0. But what if both of them are on? Well, going through an OR gate, when A is 1 and B is 1, going through an OR gate, that gives us a value of 1, but we hit that inverter, giving us a 0. Let's go back and fill in that truth table. So the easiest way to do this is to figure out A or B and then invert those values. When A is 0 and B has a value of 0 going through an OR gate, that gives us a value of 0. As long as at least 1 is true, we're going to get a value of 1. So B is 1. That meets the condition as of at least 1 value. In the third row, A is 1. That meets the condition of at least 1 value being true. And then in the last row, A is 1, B is 1. That also meets the condition of at least 1 value being true. Now that I have this, it makes it a lot easier to fill out that NOT gate. What is not A or B? Well, what is not 0? That's going to be 1. What is not 1? That's going to be 0. What is not 1? That's going to be 0. And to change things up, what is not 1 again? That's going to be 0. Let's go ahead and let's take a look at the last gate. So the last gate is XOR, and it's an exceptional OR gate, and the output is true only and only if one input is true, not both. So when you're looking at an OR gate, as long as at least 1 is true, it'll work out. With an exceptional OR gate, only 1 can be true. So it's read as A or B give output value of 1, but not both. It's written as A plus B, but that plus has a circle around it. Let's go ahead and let's take a look at the last diagram and come back and fill out this truth table. I have my input A, so I'm going to go ahead and connect that to my exceptional OR gate. I have my input B, and I'm going to connect that. Now notice the exceptional OR gate has the symbol of the OR gate, but it also has this line, this curved line right before it. That shows us that it's different from an OR gate. Now I'm going to connect this, and we have an output of 0 when A is 0 and B is 0. Now, as long as only one is true, we should get an output of 1. So I'm going to turn on B. Only B is 1, A is 0, B is 1. We get an output of 1. Now, what about if I just turn on A and do not turn on B? That gives us an output of 1. Now, remember, with an OR gate, when we turn on both of inputs, both of them are 1, the light bulb turns on. We get an output of 1. With an exceptional OR gate, it has to be one or the other. It cannot be both. So let's go back and let's finish filling out that final truth table. Filling out the final truth table for our XOR gate. As long as only if one input is true, not both, we should get an output. Is only one input true here? No, both of them are 0. That gives us an output of 0. What about when A is 0 and B is 1? That meets the condition as only one input being true. That gives us an output of true. Same thing, A is 1, B is 0. Only one input is being true here. That gives us an output of true. And this is why a XOR gate is different from an OR gate. In an OR gate, both of them could be true. But with a XOR gate, both of them cannot be true. That doesn't meet the condition of only one being true. That gives us an output of 0. I hope you found this video helpful. In the next video, we're going to take a look at 3 inputs and some complex logic circuit problems, as well as some practice exam questions so you can get practice. So if you found this video helpful, please give it a thumbs up and subscribe to help the channel grow. And we'll see you guys in the next one.